So in 1101, we learned how to go from moles to grams and grams to moles and atoms and all that in Chapter 3. We can use the same techniques to learn about gases also. So we know from Wednesday's lecture that for an ideal gas, assuming, of course, the gases have very small volumes and they don't interact, we can use PV equals nRT. That can get us the moles. Okay. Once we have moles, we can do whatever we want from back to Chapter 3. So we can calculate molar mass like we did on Wednesday. We can also calculate density. We can go from moles of one thing to moles of the other. We can go to molarity if we have volumes, like from Chapter 4. But of course, if we want to go from moles of one thing to another, we need a balanced equation. Okay. One of the things I do want to talk about, your book slightly mentions the Gay-Lussac law of combining volumes. This is just this is a statement basically saying that we can, that volumes are additive. We can take that amount, the volumes, and the density equation, which is mass over volume, related to the ideal gas law and the molecular weight, where molecular weight is grams per mole. We can rearrange these equations and we're able to relate density to the molar mass given here. So we can calculate the density of a gas. If we don't know the pressure, if we know the mass, volume, and temperature, we can also find molar mass rearranging here. These equations will be given. I would not expect you to know them. Okay. But we can relate the stuff from 1102 back to 1101 is the takeaway message. And I did include the derivation. How do we get from these? How do we go from these three equations into these final results? That's just for you to review. Again, I don't need you to know the process. I just wanted you to know that the steps, just be familiar with the end results. So let's go through an example how we can combine these terms. How do we go from the ideal gas law to moles, and what we can do with it, combining what we know from from 1101. So one of the things is the problem here. This is on your worksheet, okay? And I'll post the answers to the rest of the questions later today. But in this question, it's saying we have two gases. They are right now separated, okay, by what we call a stopcock. So that means the gases cannot interact. We have 6 liters with a pressure of 0.5 atmospheres of nitrogen monoxide. And on the other side, we have 1.5 liters with 2.5 atmospheres of oxygen. When they open, these gases are going to react and form a third gas, nitrogen dioxide. Assuming the reaction is held at constant temperature, what is the pressure of nitrogen dioxide after this reaction's occurred? So you might look at this problem and say, you have no idea what's going on. There's a lot of information. So just like we've done before, let's make sure that you have the information available. So we start with a balanced equation. Just like in Chapter 3, we learned how to balance equations. We can see that there are total of 3 oxygens, 1 nitrogen on the reactant side, but 1 nitrogen and only 2 oxygens on the product side. So we can balance the equation by putting a 2 in front of nitrogen dioxide. So that means we have 4 in order to get 4 here, we can balance the nitrogen here. So, sorry, my pen's not working. So we have 2 nitrogens, 4 oxygens on the reactant side, and 2 nitrogens and 4 oxygens on the product side. Okay. So what we can do now is step 2, which is find the moles of each reactant. And this should look familiar from Wednesday when we found the molecular weights. Here we can still start with finding the moles. So we know that the gas law is PV equals nRT. Okay. In this case, we have 2 gases, though. And so if we take the scenario before we open the stopcock, we know the pressure, volume, and temperature of each of the gases before they react. So when they hadn't decomposed or reacted. So we can assume before the reaction occurs, we can calculate the amount of moles we started with. Okay. And so we can rearrange the equation and say N equals PV RT. Okay. I'm sorry, my pen's not working terribly well on this screen. And so when we find the moles of reactants, okay, we can use this equation for both. So if we are trying to find the moles of NO2, okay, and what this just means is moles of, sorry, not NO2 in this case, but NO. Trying to get the eraser. There we go. There we go. Then we know that the pressure of NO started out as 0.55. Oh, sorry, zero. Ooh. New computer. Please bear with me. So 0.500 atmospheres. The volume is 6 liters. Again, since we're dealing with atmospheres, we're going to use the value of R as 0.08206 atmosphere, liter, mole, Kelvin. Times the temperature, right now it's at 25 degrees Celsius, but we know from Wednesday's lecture we always have to convert to Kelvin to maintain a absolute scale. So that is 25 Celsius plus 273, which would be 298. That's a 1.5. Okay. So when we work this out, what we should get is in your calculator, you should get 0.1226 moles. Looking at the significant figures, once we add the 2 or the 25 to 273, we're going to have at least 3 sig figs. So we say that this is equal to 0.123. Okay. But since we're going to use this value later on, what we're going to do is keep a notation of this 1.226, keeping that low. You can also underline or something like that. So if you think about your lab reports, because we want to avoid rounding issues. Okay. We can do the same thing to find the moles of O2. This time, instead of writing the gas in parentheses like you saw in example 1, I wrote it as a subscript. Either notation is fine, and I just wanted you to be familiar with different ways of representations. Here we can see that the moles is, the atmospheres of oxygen was 2.50. We have a different liter. It only started with 1.50 liters. The gas constant is going to be the same. And the temperature is going to be the same at 298.15. I kept a few digits there. When you put it into your calculator, you will get 0.15327 and so forth moles. We only want 3 sig figs, but we're going to keep an additional digit for rounding purposes and say 1.532. Okay. Moles. So now we have moles of things. Great. But what is the question actually asking? So it wants to know the pressure of NO2. So we have moles, we have balanced equations. So if you think back into chapter 3, if we have moles of, or the amount of reactants, and we want to know the total amount of products formed, this is an example of a limiting reactant equation problem. So we need to compare these two moles of gases, of reactants, and see which one will run out first, which would be our limiting reactant. So we can see here, this should be a 3. You see here now I have 2 moles. I have the moles of NO and O2. Okay. I also need to know how much NO2 is produced. And remember, if we go from moles of one thing to the moles of the other, we have to find a mole ratio. So what I've given you is the moles that we just calculated and the mole ratios from the balanced equation. Okay, we know that 2 moles of NO produces 2 moles of NO2. 1 mole of oxygen forms 2 moles of NO2. So we start with what's given. Okay. Make sure your units cancel out. So now we know how many moles of NO2 is formed from NO and from O2. And in this case, we're not measuring out the grams. It didn't ask how many grams we want pressure. And so back to our equation, we know that the moles, the ideal gas law, we're looking for moles of NO2. So looking through, we see that NO2 can produce a maximum of 0.123 moles of our products, while the amount of moles of oxygen produce 0.307. So the one that's going to be running out first is NO. Okay. So NO is our limiting reactant. That means no matter how much oxygen is added, how much extra oxygen there is, we will only form the max amount of NO2 being 0.123. So this is in excess. Okay. So now we know the moles of NO2 when the reaction has occurred. We can go on to find now the pressure of NO2. Okay. We use the same gas law. Okay. Now we rearrange it. We don't care about moles. Now we're trying to solve for pressure. So we went ahead and calculated the amount of moles of NO2. The gas law constant stays the same, and the temperature remains constant. The thing that is different is now we're dealing with the total volume. Oh. So the total volume tells us, I'll just not write out the word total, is because once the stopcock is open, that is when NO and O2 interacts and forms. And so now we have a total volume of 6 plus, basically 7.150. So our pressure of NO2 is here, 0.401.